Hello. All right. Oh, you guys are here. Excellent, excellent. Hello. All right. Hello. I don't know if you can hear me, but hello, Dante. Hello, Juliana. Hello, Jay. Hello. Good. All right. Hello, Bradley. Hello, Mario. Hello, Bree. Doing chat now. Oh, more people. Yes, good afternoon, Juliana. Hello, Samantha. Hello, Mario. Good afternoon, Valentina. Hello, Christina. Good afternoon, Bradley. Good afternoon, James. Good afternoon, Bree. Hello, Dante. Good afternoon, Key. Oh, and more people. Okay. Okay. All
Good
right.
afternoon, Professor.
Good afternoon, Christopher. Thank you. Awesome. Awesome. All right. We're totally rolling. We're in business. Okay. Thank you all for rolling with all of these schedule updates. Very quickly, I appreciate how flexible you're all being. You totally get it. I get that the comments and the questions that you submitted last night from the two videos yesterday really actually helped a lot. They were very specific. I mean, it's clear that you guys watched the video. I'm going to try to get to some of those questions that you asked. I may not get to them all today, but I'm good. But they're great questions, and it's great to see what you did actually understand from the video. I really appreciate it. Good afternoon, Alexa. All right. Oh, and more people coming. So I think we're all together on the same page. We're going to be quick today, as I made clear before. Did I say hello, Alexis? Yeah. Okay. So a quick one. Good afternoon, Allison. Okay, excellent. A couple of logistical announcements. As always, I definitely do not have your exams back yet. I apologize. I sort of anticipated this. You will get them, of course, when you get them. But that's not happening right now. More people coming. So it's all about Doppler effect right now. I know you just did a lab about it, board meeting about it. I know that's what happened. I haven't heard what happened in it. I'm sure some things are clear, some things are not. But what I'm about to do right now is literally go through the four cases. I'm going to walk you through how you do the four cases. I'm not going to do all four right now. Oh, good. Oh, excellent, Samantha. Thank you. Oh, good. Okay. So maybe this will even be redundant for some of you or unnecessary, but I'm going to give you my version of walking through a case. Of course, I'm going to emphasize that once you really know how to do a case, you do the same approach for all cases. The ultimate goal, and you maybe already found this out in lab. Good afternoon, Tuiba. Excellent. The ultimate goal is to contrast and compare the findings from the four cases. Very interesting conclusions can be drawn from the relationships among the numbers. Maybe you already even did that in lab. I guess we'll find out in a second. Well, we'll find out. But since we have limited time today, what I want to say is, number one, the homework that was due today, which was really to do those four cases, was basically the same assignment as the board meeting. For whatever it's worth, I'm extending, you might have noticed, I just extended that deadline till tomorrow, partly so that when we end early today, which we're going to do, I mean, I'm going to end early today as I suggested. I'm going to end early today, and then my big request is one way you can use the extra time is if you guys have a Discord server or something like that, or if you have a way of communicating with one another right after I'm done, to extend homework, I would definitely suggest that you help each other and try to finish that homework, the four cases of the Doppler effect, for tomorrow night, because as I keep suggesting, one thing that definitely always is on the final exam is exactly this topic, this issue of knowing how to compare and contrast four cases of the Doppler effect. So you see it's coming at you from all angles, from the lab, from the lecture. Today, I'm going to give you my walkthrough. Hello, Dennis. Good to see you. And I'm going to start it in a second, I guess. And we're going to, as I say, we're going to end early. We're going to end at like 5, actually, for those people who want to plan. And as suggested, I will later post more video material at some point tomorrow during the weekend, but you'll have all weekend to watch it. Again, also remember that the other homework assignment that in principle is due Monday, the one on tone, that is extra credit, so to speak. I mean, all of this is extra credit, but that one is you're doing for points. We may or may not ever talk about it. But and you use whatever resources you want to do that one that's due Monday. But it's totally for points and for knowledge and for future science classes. It's not something, it won't appear on the final exam. Okay, good afternoon, people. Hello, hello. Okay, so I want to get rolling for like, you know, the next 45 minutes on this Doppler effect thing. I think, okay. Fair enough. Okay, good. Glad to, I mean, I see what Christopher's saying in the chat. Fair enough. I mean, I have to do a mix. I mean, I'm not good. I'm glad to know it's not that upsetting. Okay, cool. Okay. So that's what we're doing. We're not going to do it all the time, but good. That's what we're doing now. And I will say, you all seem to really get a lot. I'm impressed how much you seem to have learned or absorbed from the videos that I posted. So cool. So today will be short. Yes. Okay. It won't always be like this. We only have 2 weeks left anyway, but today will be short. Oh, sorry. So last question I want to ask you before I get this rolling. In lab today, how many cases were you able to solve in groups? All 4. Oh, okay. Interesting. So maybe this will be even shorter than, wow. Okay. And thank you all thank you, Allison. That's very interesting. So you actually really did. Wow. Even the bonus. Huh? That's great. Well, all right, wait a minute. Maybe we can cut to the chase here. I'm going to switch to the board just to, and these equations on the board, then look from it. Wow, I actually learned something. Well, if Chris actually learned something, then okay. Wait a second. I'm going to slow down then for a second. Maybe this is, and as I say, from all your comments on the last couple of videos and all your feedback so far, it does seem like you guys do know what's going on. All right, so let's talk. Maybe we'll talk about this a little bit more informally then. Maybe I don't have to blast through. So let me ask you, first of all, these equations on this board, they're familiar then? Wait, huh?
Yeah, they're familiar.
Oh, and okay. Oh, and the thing, Samantha, that's very nice. But I didn't even think but the video I posted wasn't even the one that actually shows you how to solve. But okay, no, great.
No, you did. Like at the end, you started actually doing math, like you said. But you only did it for one case. But like earlier in the video, you like said each case was X, Y, and Z. So it was basically, once you did the first one, the other 3 were straightforward, I guess.
Okay, actually, wait, this is a great relief. And I'm going to slow down. I'm really pleased. Really. And it's true, when I rewatch that video for myself or re-listen so that I could give you guys the timestamps and all that, it's true that then I ran out and I didn't hear the last 50 minutes. So I was worried that I never got to any math at all. So I did do one case. Okay. And you were able to extrapolate that case to the other cases. And look, I'm impressed. I'm happy. I mean, and maybe it all seems obvious to you guys, but not everybody can always do this on their own like that. So, all right. So I'm going to slow down for a second or speed up. I mean, I'm going to calm down for a second. I'm going to ask you then, but I'm really pleased to hear this. That's great. So I'm going to ask you then the case of receiver approaching. Could you guys, tell me here. Okay, let's actually go over this. Instead of me just blasting through, let me hear what I'm totally impressed. Let's establish this first of all. In the case that you did for lab, I mean, in the situation you did for lab, you stop me when I'm doing this wrong. This is my impression. You have let's do case 1. I mean, I'm not going to walk through them, but now I just want to get some answers from what you guys got, because this we can get to the chase. I'm going to call case 1 the receiver approaching. I don't know if that's actually the case that you did first, but I'm going to look at that case first. In that case, for your numbers in lab, if someone first of all, I assume, tell me where I'm wrong. I assume you have that I'm listening.
So we were giving a frequency of like 500, I think.
Okay. Sorry.
But
okay.
In this case, we got a higher frequency with the receiver approaching.
Awesome. That's great so far. Wait, slow down though. Before you even give me that answer. Okay. The frequency of the wave according to the source was 500 hertz. And I assume the velocity of the wave according to the medium was 340 meters per second. I'm assuming that. Can you tell me what was the velocity of the receiver relative to medium in your case in lab? If you know what I'm saying. Do you know what I mean? Like, just remind me what the given was for you in your lab. Like, what was, it's in the chat. I'm sorry, I was writing, I didn't see the chat. 44. Okay, 40. So the velocity of the receiver according to the medium, I mean, relative to the medium, was 44. Great, thank you. And you agree with the 340, and then Christopher said the 500. Okay, and I'm going to cut to the chase. This is good. We're going to save a lot of time. Then I'm going to, before I go any further, and before Christopher tells me an answer or something like that, are we all cool with, in this case of receiver approaching, and again, I don't care which is case 1 or case 2 or whatever, but in the case of receiver approaching, are we all cool with my designation that I'm, before I even put in the numbers, I'm saying that the direction in which the wave travels, I'm calling that positive. I'm calling anything against that negative. Like, this goes back to the whole Hema-Walters, like, definitely put in a coordinate system thing first. I'm calling the direction of the wave positive. Therefore, to cut to the chase, in this case, it seems to me that the velocity of the receiver relative to the medium, I'm going to call negative because the receiver is going in toward the source. It's going against the direction of the wave. Like, before we go any further, are we all cool? Like, yes. Okay, thank you.
Yeah, I'm fine with that.
Okay, great. Okay. So this is great. So yeah, I'm going to skip. It's you all did already. Can you, either Christopher or anybody, tell me, so for these givens, what answer you found for the frequency of the wave according to receiver?
So we got what, 564.708 or something like that. But
Okay.
you can just run it to 565.
Awesome. I will. Thank you. Okay, 565 hertz. Okay, that's awesome. And you're all agreed. Like, you're saying you got that in your group, then you all got into a board meeting circle, and as a class, you even all agreed with that. That's what you're telling me. Is that right? That's awesome. Oh, this is really gratifying, people. Okay, it doesn't usually work out this well. Okay, so 565. So first of all, that sounds good to me. And yes, as I think Christopher already implied, or somebody already implied, that is certainly intuitive that this frequency as measured by receiver is higher than the frequency as measured by the source. Like, I like that result because the receiver is running in toward the source. And it sounds like you like that too. I mean, I'll check the math in a second, but that result sounds good to me. One thing I want to clarify, because I did read, the comments you guys made on the video the night before. I want to make it clear right now, in case anybody had a different feeling in the board meeting, like, that 565 is correct to the receiver, and the 500 is correct to the source. Neither one is more correct than the other. Like, this is a relativity phenomenon. Every answer is correct in its frame of reference, and no one frame of reference is more legitimate than another. Are we clear on that? Oh, no problem. No problem.
That's good, because we all agreed on that too in the discussion board, saying that it was based on relativity and like none was correct compared to the other. So that's good.
Awesome. Okay, that is good. And I see that Allison's saying that in the chat also. Okay, great. No, we're really progressing here. Okay, so you got that. Now, I guess I'll go a step further and just ask. And yes, if you already did it, I'm not going to walk through the math now if everybody's comfortable with the math, but that's great. Okay, then I'm going to ask, which one do I ask? Okay, and what did you get when you, for let's call case 2 receiver receding, right? So all the same numbers, but the thing, the receiver going away from the source. So the only thing that changes there is that I would call the velocity of the receiver relative to the medium, I would now call that plus 44. So when we did that, what number did, Are you going over homework 4 today? Wait a minute. No. Wait, homework 4. Oh, this is homework. Well,
No, this is a lab.
This is the lab.
This
Right,
course.
right. So the person who's asking in the chat, am I going over homework 4? I'm not doing I was going to. Well, I'm giving you an extension on homework 4. I want everybody to hand it in by tomorrow night and work together on it. But I will say that homework 4 is exactly this, just with different numbers. So what I'm doing, I'm just answering someone in the direct chat. What I'm doing now is getting your answers and checking them myself from the lab today. It sounds like everybody had a good, confident, successful experience in lab, and assuming that's right, and we're all clear in the lab, homework 4 is literally a repetition of the exact same thing, just with different numbers. So, I mean, the answers, I'm not explicitly going over homework 4 right now. I'm sort of preparing you to be able to redo it if you want. But this is the lab. It's the same numbers, the same situation. I mean, different numbers, same situation. Okay, but so I hope that's clear, direct chat person. But okay, so in case 2, where the receiver is receiving, does someone, maybe someone knew, oh, you got, great, thank you, Samantha. So you got that the frequency of the wave relative to the receiver there is for approximately, okay, 435 hertz. Now, let me just want to check one thing. Yeah, so I don't know if this came up in the board meeting or not. Again, I'm just going, this is an overview now. I'm like taking your information and I'm going to make comments and questions about it. But so far, I would say this. The first number, I didn't do all the math in my head yet, but the first number strikes me as reasonable because it's higher than 500. And I might add it's noticeably higher than 500, but not ridiculously higher. And that makes sense because the speed, 44 meters per second, is a noticeable fraction of 340, but not a preposterously high fraction. In other words, the bigger the speed that either object is going relative to the wave speed, the bigger a Doppler effect there is. So I find the number, I'm not saying right off the top of my head that 565 is definitely right, but I'm saying it's certainly reasonable. Now, if we go to, and I can check before we're done with class, but now if we go to case 2, and you tell me that in case 2, the frequency of the wave relative to the receiver is 435, I have to say right off the top of my head, well, that's solid, that's perfect, assuming 565 is right, because you notice, I don't know if you noticed this in the board meeting, but look, you're telling me that when the receiver goes away at 44, rather than come in at 44, the frequency drops down by 65 hertz, as opposed to going up by 65. In other words, the two answers are equidistant around the midline of 500. That's very intuitive to me. And in fact, that's always the case with receiver moving relative to medium. So, right, so I'm looking at, so I love it. So far I'm totally with you. So I'm just saying note. I'm saying note. Like that makes total sense. Now I want to ask the sort of more interesting question, or sort of the point of all this. If we go to case 3 now, what I'm calling case 3. Oh, I didn't mean to. No. Well, this was meant to be on the, anyway. If we go to case 3 now, which would be, say, source approaching, right? So in this, now let's be explicit here. I'm very interested to hear what you guys said about all this. This is right, the same situation, right? Except the speaker, which is still emitting. So the speaker is still emitting a sound of 500 hertz relative to it. But now the receiver is not moving at all relative to the medium, right? This now the velocity of the receiver relative to medium is 0 meters per second. The velocity of the wave relative to the medium is still 340 meters per second. But here now, if I remember correctly, if I understand correctly, we now are saying that the velocity of the source relative to the medium is now 44 meters per second. And I'm calling it right from the get-go. If I'm still assuming, which I am always for all of these Doppler effect problems, I am pre-designating the direction of the wave as positive. And anything, oh, that's kind of weird how I wrote that. The direction of the wave is positive. Anything against the wave is negative, right? So the velocity of the source relative to the medium seems to be positive 44 meters per second. Okay, that's the setup now, right? And I'm gonna pause. Well, yeah, okay. I'm just gonna ask. I mean, if we were in lab right now, I would ask you to make a prediction before you even do the calculations. I don't remember if the lab did ask you to do that. If we were in lab, I would ask you to literally predict this number before you even do any calculations. However, I mean, that's a little silly now because you've done the calculations. So what did you get for this case for source approaching? For you, I'm looking. Okay, the lab. Okay.
574.
Awesome.
That's what I
Okay.
got.
Okay. So I hear Christopher, and I see Samantha, and I see Juliana, and I see Valentina. Awesome. Thank you all. And again, if you're just, you can still participate. I mean, it's not a race. So if someone else also wants to put in the chat, that's great. Okay. Very interesting. I have to. All right. So you got that F of wave relative to receiver here is approximately 574. So let's pause here for a second and note, and again, maybe this was your discussion, but let's note that that is definitely different from 565. I mean, it's definitely different, right? That's it's close, but that's not a rounding thing. I mean, that just isn't around. It's, you know, it's 11 digits off. That's not a rounding thing. That is different from 565. Like 565, it is greater than 500. So it's reasonable. Like these two, one of these two objects is coming in toward the other. This is as though we were standing at Coney Island or Far Rockaway or whatever, and the boat that's making the waves is like driving into us while it makes the waves. Like it does seem intuitive to me that if something that's making waves is coming into me as it's making them, then I would encounter those waves more frequently than if the source were just sitting still relative to the medium. Like I like this, but it is interesting to me that this number is different from case one. And I will even admit, I don't know if you were asked to predict or not, but if I were asked to predict, if I'd already solved case one and I hadn't yet solved case three, I personally would have totally predicted that they'd be the same answer. In fact, I'm even going to tell you why I would predict that, because this whole thing is based on relativity. This whole thing is about the fact that velocity is a relation between two objects. It's not a property of one object. So, right, like the Earth can say that the sun is moving to the west relative to it, or the sun can say that the Earth is moving to the east relative to it, and they're both correct, and neither one is more correct than the other. So I would have thought personally that since this whole phenomenon is not only part of physics, which all obeys relativity, but since the phenomenon explicitly derives from relativity, I would have totally thought that a source driving in toward a receiver would yield the same result as a receiver driving in towards a source. So I find it very noteworthy that the number we get for case three is not the same as case one. I'm not trying to trick anybody. I'm just saying all that. So now I'm looking in the chat. Okay, Alexis, awesome. So Alexis is saying she would have thought that as well. Well, thank you for your honesty, and thank you for being in the same club as me. So, okay, so cool. And I'm not being sarcastic. Like, so can I ask you guys, if you got these two different numbers, I mean, did you discuss, if it did surprise at least one person, did you get a chance in the board meeting to, I mean, did it come up? Did anybody challenge this second number, or did anybody, oh yeah, go, okay, go, sorry.
Because we all got the same thing, so it wasn't much a challenge, because we're assuming that, okay, seeing that we're all on the same page, we did it correctly, so.
Okay, oh, sorry, go on.
No, I'm done.
Okay, so first of all, that's totally fair. On a lot of levels, that's totally fair. And I will say, I'm not trying to trick anybody right now. I will say this, the very reason, well, one of the many reasons we make a big point of Doppler effect is exactly this issue, that there's something going on that case 1 and case 3 don't have the same answers. And I'm going to stop right now. And I'm going to assume from what that you also got different answers for case 2 and case 4. And this is kind of the topic. This is the issue. Now, a couple things though. First of all, the fact that you all got the same answers for all these cases, and the fact that, like, yeah, you accepted them because you were all getting them, that is to your credit. Honestly, the fact that you understood the method well enough, I mean, this is unusual. This is totally hats off to you, especially without me being there, whatever, that you guys understood the method enough from that video or from wherever, and you took the method that you applied the same method carefully and explicitly enough to each of the 4 cases, and you somehow didn't warp it or distort it to force similar answers, is totally to your credit. Like, somehow you were really, and this is unusual, you were being very scientific. If you turned that crank carefully enough that it spat out these 2 different, basically I'm saying you're right. I am saying you're right. And you were right to trust your results, because apparently you did. A lot of people in this situation would kind of, like, without realizing it, they would sort of change their method to fit what they kind of wanted to happen. And maybe that didn't happen because we didn't make a prediction first or something, but I am impressed. Truly, first of all, I'm just impressed that you got through this much this fast, really. Second of all, if you all got this different answer for case 3, it means you should have. That was correct. It means you were doing the method right. So yay, and praise be unto you. Now, let me say, here we are. If we're all together now with a few more minutes left, I do have to, there is something weird about that. There's something that has to be reconciled. Like, why would, besides the fact that the math says so, like, if at least Alexis, if not other people, sort of see my point that, and I'm not trying to trick you, I'm saying something is being revealed here. Something tricky is happening. That if the receiver runs toward the source, there's one Doppler shift. If the source runs to the receiver, qualitatively, we get the same Doppler shift. But quantitatively, precisely speaking, we don't get the same Doppler shift. Like, right, the difference in the frequencies is different for the 2 cases. Somehow, there's a difference between me running to you while shouting versus you running to me while I'm shouting, even if all the numbers or all the magnitudes are held constant. So what I want to pause and ask, and again, you're just saving me time. Like, I would have thought that this whole 40 minutes I was going to have to, like, walk through all this computation. I'm so glad that we can get straight to the point like we are right now. You all the more deserve, like, to get the time off afterwards. But here is the discussion question. How can it be? What is going on if this is all based on relativity? Why is source relative to receiver somehow yielding a different result from receiver moving relative to source? Like, and I'm open to, like, anybody wants to put in the chat or direct chat or say anything. That is the, and it's not a trick. It is the question. I'm looking at the time.
Wait, what was the question? I'm sorry.
Okay, so the question is, the question is, how, if this whole thing is based on relativity, right? And if relativity specifically means, like, here, let me go back on the board. Hold on a second. Like, and again, I'm not trying to trick you. I'm trying to say that something tricky is going on. If you look, the meaning of relativity is those 3 equations right there on the front board, right? And very specifically right now, I'm saying part of the meaning, like, let's back it up for a second. Those 3 equations are the 3 different cases of relativity. Case 1 is when you have 1 object. Case 2 is when you have 2 objects. Case 3 is when you have 3 objects. Like, just to quickly remind you, and then I'll repeat the question, but to remind you, the essence of relativity is saying that velocity in physics across the board is not a property that one object has. Velocity is a relation between 2 objects. Like, that is the fundamental breakthrough of classical physics. Honestly, like, all of physics 203 and 204 and Einstein relativity and all that is ultimately based on this idea that there's no such thing as speed. I don't have speed. I have speed relative to you. or I have speed relative to the Earth, or I have speed relative to the sun. And depending on what frame of reference you pick, you'll get, different numbers for my speed, and they're all correct, right? But bottom line, I'm saying speed, velocity is a comparison. It's not a description. And mathematically, what that means, these three equations right here, mathematically, what it means is like the speed of the velocity of me, if we only have one object in town, if there's only the Earth to talk about, the velocity of the Earth by itself, relative to itself, is necessarily zero. If you've got nothing to compare it to, then it's not moving. But if you got two objects, now here's where I'm going to now to answer Christopher's question, to repeat what my question is. The second, if you have two objects involved in relativity, if you have two objects involved in a physics situation, what relativity says is the velocity of one object relative to the other is just the inverse of the velocity of the other relative to the one, right? Again, you can say that the Earth goes past the sun at 65,000 miles an hour, or you can say that the sun goes past the Earth at 65,000 miles an hour. Both are equally legitimate. Both are equally true. It's just a perspective question of which one you assign 0 and which one you assign 65,000. So what I'm asking, and then the third thing that velocities add in the way that they do if you have three objects. So what I'm saying to everybody, what I'm asking, and I see there's one thing in the chat, I'll look at it in the chat. What I'm asking everybody, or what I'm repeating for Christopher, is if we base this whole Doppler effect phenomenon, if all the number crunching and all of the effects that are happening are based on this idea that velocity is a comparison between two objects, and that comparison is always symmetric, right? If I run to the east past you, then you are running to the west past me at the exact same number, whatever that is. If velocity is always symmetric like that, like Roman numeral 2 in this equation here, then how can it be that when the receiver runs toward the source at 44 meters per second, we get one resulting number for the Doppler effect, but if the source runs toward the receiver at 44 meters per second, we get a different number for the resulting Doppler effect? Like, this is my question to the whole group. I am challenging you. I'm not arguing with you. Your numbers are correct, actually. I'm impressed. But something is very weird that case 1 and case 3 don't get the same answer. That if you go like this, you get one answer, but if you go like this, you get the other answer. Why should that be? I would think if this is all about relativity that we get the same answer. That's my question, but I see the chat lights are lighting up, so I'm looking. Hold on. Okay, wait, so, some of them are private chats. Let me just look. Okay, hold on. Wait. Wait, interesting. Okay, one question in the direct chat is frequency also a property of, or let's say a consequence of relativity, or is it like acceleration? That's a very good question, because it's true. Everything I'm saying about relativity applies to velocities, but it does not apply to acceleration. That is true. But the answer is yes, frequency is affected by relativity. It is more like velocity than like acceleration, because that's what this whole Doppler effect discussion is all about. That frequency is relative. The frequency that I hear or measure in my frame of reference is not the same as the frequency you measure in your frame of reference if we're in two different frames of reference. If we're moving at two different speeds relative to the medium for a wave, then we will measure two different frequencies, and they're both correct. So just to answer the person in the direct chat, frequency is relative, just like velocity is relative. Good question, but the answer is yes, it is. Now wait, there's another thing in direct chat. I'm just reading it again. Oh, okay. Someone is saying something that's going to get us on the road to resolution. Someone is saying something in the direct chat. I'm going to read it, or at least part of it, out loud in a second without saying the person's name. But let me just ask this before I read. So one person in the direct chat is sort of helping to start us resolve this question. But let me just make sure before I read it. Honestly, again, I'm saying interesting. Okay, another person in direct chat is saying something that is helpful and might possibly resolve this. Can I just ask you again, though, God, just to make sure, honestly, In fact, don't even raise your hand. Just put in the direct chat. If you basically, even if you don't have an answer, if you basically think you understand the question I'm asking, if you see the issue that I'm worried about, even if you don't have an answer, can you in the direct chat either say something like, yes, I see the question, or say, no, I don't get the question in the direct chat, please. Like, you don't have to answer it, but I just want to make sure. Okay, yeah, okay, I'm going to wait for it. Okay, cool. Pretty sure. Okay, cool. All right, great. I love it. Oh, okay, that's honest. Okay, a couple people don't understand. Okay, I do love this class. I love the direct chat. Okay, a lot of people answered. A couple people in direct chat said that no, they don't understand the question. So I'm just going to try to rephrase it one more time. Basically, but then we'll try to answer it. I'm saying, I'm asserting that the fact that the answer you got for case 1 and the answer you got for case 3, you got 2 different answers. I'm saying you are correct. You do get 2 different answers for case 1 and case 3. But I'm saying, if you really think about it, that's weird, or at least it seems weird. It should be slightly surprising because case 1 and case 3 are all the same numbers. In one case, the source is moving in at a certain number. In the other case, the receiver is moving in at the same number. So the only difference between the 2 cases is like whether the pitcher is running into the catcher or the catcher is running into the pitcher. I would think from my experience in physics, or certainly my experience from relativity, I would have thought that those 2 situations would lead to the same result, because like if, this goes back to your stuff from physics 203, if an Audi passes a Buick on the highway, I mean, if the Audi passes the Buick at 30 miles an hour faster than the Buick, then the Buick will see the Audi going 30 miles faster than it, and the Audi will see the Buick going 30 miles an hour slower than it. They're still going to get the same number. They're just going to disagree. Like, the Audi's going to see the Buick going backwards. The Buick will see the Audi going forwards, but they'll both see it at the same number. So I just would have thought that whether the source is coming in or the receiver is coming in, that they would end up seeing the same phenomenon. So I would have thought the Doppler effect numbers would be the same, but we don't get the same numbers. That's my question. I mean, maybe that's still not clear, but now I'm looking, there's more things happening in the chat, but that's what we're trying to resolve. And that's our big goal for today, for the next 18 minutes, is just try to unpack how could that be. All right, so I'm looking, there's things. So hopefully the people that told me in the direct chat they don't get the question, maybe hopefully you'll tell me if that helped a little bit. But all right, I'm looking in the direct chat. The source is moving towards the frequency. Okay, I'm not going to read all these out loud because they're good. Everything, if you put something in direct chat that was an attempted answer, you're definitely on page with me. Yes. Wait. Oh, wait. Okay. And one thing to clarify. So somebody put in the direct chat. Yes, to clarify this, everything I'm saying right now also applies to case 2 and case 4. Like when the source is going away or the receiver is going away, same thing happens, that you get 2 numbers that are both below 500 as you'd expect, but not the exact same number. I mean, that's totally correct. Someone's saying in direct chat. So yes, we could. I'm not saying there's anything special about approach, whether it's approach or recede. What's funky is that it seems to make a difference whether the source is doing the moving or the receiver is doing the moving. That's what seems interesting to me. Okay, I'm looking. Okay. Oh, I'm pretty sure you get the question. Okay. I'm looking at there are people saying things in direct chat. I'm going to, let me just see if let me pause for a second to see if I should say this or write it down. All right, I'm going to write down. Okay. Oh, there's more in the direct chat. Hang up, bear with me. Whoa, a lot in the direct chat. Okay. Okay. There are very, very thoughtful, interesting things happening in the direct chat. I think what I'm going to do, and they're all like helpful and they're all getting us toward the point. I'm not sure if it will fully land the plane for everybody. What I'm going to do, and again, we have like 16 minutes. I'm going to read the things out loud in the direct chat. I'm not going to say the names, but I'm going to read them out loud because I think they are helpful and they all definitely show an understanding of the question. And then I'm going to put the answer my way on the board. But what people are so, and there's more in the direct chat. Oh, wait, okay. And obviously all of you who are putting things in the direct chat, definitely submit for points and all of that for real. But I do really like the discussion. Okay. All right. I'm going to read this out. Also, I'm gathering just from the way I'm asking this question, I'm gathering this was not the big subject of your board meeting. I'm gathering. I mean, this is seems like a slightly new question, which is good. So we're not wasting your time. All right. I'm going to just read out loud what I see in the direct chat. So I see, I'm guessing the source is decreasing in displacement toward the receiver. Let's say when the source is at rest and the gap between each wave crest is say 5, but when the source moves along the wave and creates the wave at the same time, the gap is slightly smaller, creating a higher frequency. So one person is suggesting that it has something to do with the fact that when the source is moving relative to the medium, that something's happening to the wavelengths. Note that. That's a good point. I'm going to develop that. I'm going to expand on that in a minute. Then someone else in direct chat saying, is the time between the crest changing? And by the way, definitely the answer is yes. The question is, why is it changing differently in one case versus the other? I also on that, and now it's very phrasing things in terms of Doppler effect can be very tricky. Like the English can get very, very complicated very fast when we're talking about the Doppler effect. One thing I want to clarify to all of you before I go any further, in the same way that we all understand, it seems like we all understand that that whatever the receiver measures and whatever the source measure in a Doppler effect, they're different, but they're both correct, right? Like when the motorcycle goes past you in Manhattan and you hear, right? You hear those two different sounds, like they're both legit. And the entire time when you hear, the entire time the motorcycle is hearing a pitch in the middle of those two. The motorcycle is just hearing, right? And it's not like one person's right and the other person's wrong. And if you put tape recorders, by the way, or whatever, if you took your iPhones and you recorded the sound you hear from the motorcycle and the motorcycle gal recorded her sounds, and then you put the iPhones next to each other after the fact, like on a table, and played the sounds would be totally different. Like it's not an illusion. It's one thing I want to clarify. It is not an illusion. It's different measurements on the same reality. But also I want to clarify, as long as someone said, sometimes people call the Doppler effect a Doppler shift, or sometimes people will talk about changes. Just to be clear, if we ever use the word change or shift, what we just mean is a change or shift from the number that the source gets versus the number that the receiver gets. No one's trying to imply here that anything is changing as the wave travels. Like the wave is not changing in its character while it travels. It's not speeding up or slowing down or compressing or anything like that. The wave is doing a thing, but how it's being measured or experienced is one thing from the source's perspective and a different thing from the receiver. I'm not saying anybody got that wrong. I just want to clarify. Like that's why the word shift is a little misleading. It makes it sound like something is shifting progressively in time while this phenomenon unfolds, and that is not the case. Last way I want to put it, just to clarify for everybody, this entire phenomenon is velocity dependent. It is not position dependent. It has nothing to do ever with how far away anything is from anything else. I just want to make that, and I'm not saying anybody said it does, but I just want to make it clear, like, it's not like as you get closer, something starts to shift more and more or something. It has nothing to do with anything being close or far. It's 100% to do with how fast one object is going relative to the medium and how fast the other object is going relative to the medium, just to clarify. Now, okay, I'm going to just keep reading the direct chats out loud. And obviously, with 11 minutes left, my goal is to just get my view of this on the board before we go. But I'm just reading out anything else that's in the direct chat. So if the source is moving, I'm just reading direct chat out loud. If the source is moving toward the receiver, the frequency of the wave will be higher. Yes, as long as by that we mean, if the source is moving toward the receiver, the frequency of the wave as measured by the receiver will be higher than the frequency of the wave as measured by the source. Like that is a truism. I'm sure that's what the person meant, but I just want to clarify for it, right? Like nothing is like just higher or lower than anything. But yes, when the source is moving to the receiver or the receiver is moving toward the source, what absolutely the receiver will measure a frequency that's higher than the source measures in both cases. It's just that our dilemma is, our intrigue is why is it higher by two different amounts, depending on whether it's the source moving the receiver? Like that's the issue. But, and yes, I agree that shorter wavelengths have higher frequency. Someone wrote that in the direct chat, and I definitely agree with that. I mean, assuming a given wave, yes. Then someone wrote, even this, okay, I already read that out loud. Okay, when the receiver, okay. Now I'm reading one more. There's a couple more chatting on, and I'm watching the time. I do want to give you sort of like my answer before we're done, but when the receiver moves close to the source, as the receiver approaches the source, it catches up to the successive wave fronts, leading to a higher frequency being observed. I think that is due, I'm just reading someone's chat out, but this is interesting. I think that is due to the distance between the wave fronts being shortened due to the receiver's motion. When the source moves close to the receiver, when the source approaches the receiver, it effectively outruns the wavefronts, leading to lower frequencies being observed. Interesting. Wait, lower frequency being observed? I'm not sure I understand that, but okay. But because of the distance between the wavefronts is lengthened due to the sources. I think that's backwards. I think it's when the source goes away. But one huge theme in the thing that I just read out loud that you may or may not have caught, one huge theme in the thing that I just read is the same theme as in at least two others that I read, which is that what some people are saying here is that when the source is moving relative to the medium, something seems to happen to the wavelength, which doesn't seem to happen when the receiver, when the receiver is moving. And that is true. I'm going to spell that out in a second on the board, but they're on to something. Something about this has something to do with wavelength. Yes. I'm just reading more, and then we're going to, if the source is moving with it, which changes the velocity experiences, wouldn't it decrease if the source is moving toward the receiver? Why does the frequency increase if they are proportional? Someone wrote, and that is kind of my question. I'm not sure entirely what that means, but right. I mean, my curiosity is, I would think as long as the source moves and the receiver, or the receiver moves at the same rate, I would think some sort of proportionality thing would happen and that you would get the same effect either way. But somehow we don't seem to. There doesn't seem, I'm not sure what proportional to what this person's saying, but right, some expectation of proportionality seems to be vanishing here. Okay. Okay. We're going to get to the chase right now. And in fact, I'm going to ask you to now, I love what's in the direct chat. I'm going to ask you to hold it from here on in because we got like 7 minutes and I'm going to resolve this now, but this is great. I'm really impressed. One thing that I just read that just came in the direct chat is, and this is the nub of the part of the nub of the gist. Someone wrote, wait, wouldn't the wavelengths always be the same though? And that is a very good, that is the paradox. I'm going to tell you right now, and I will start writing on the board. On the one hand, the resolution of this, I think, does have a lot to do with wavelengths. On the other hand, that's not a simple thing to say or to understand because, oh yes, if you look at the method that you all did to solve all 4 of these cases, the main thing you were assuming in step 2, in every case, the whole method is 3 steps, and step 2 of it is explicitly assuming that the wavelength according to the source is the same as the wavelength according to the receiver. That is absolutely correct. And that's again what I'm saying before. Don't assume that something's sort of changing on the way from the source to the receiver. Nothing's changing on the path from the source to the receiver. They both must agree on the wavelength. That is, in fact, the only thing. That's the thing that they both, the source and the receiver, will agree on is the wavelength. So there's something bizarre is going on here, and I will explain because I know we're running out of time. I'm just loving what's in the direct chat. Also, to the constancy. Wait. Well, okay. One person is saying something very like wise and interesting, fascinating in the direct chat, but they're talking about special relativity. Just to be clear, every time I say relativity, I mean I mean Galilean relativity. I mean relativity from Galileo and Newton. I mean the relativity of velocity itself. I don't mean Einstein relativity. Once Einstein adds the idea that the speed of light is always the same, then relativity takes on a whole even richer meaning. It has to do with, I'm not talking about that yet. That's certainly at the end of the course. I'm just saying the fact that velocity is a relation between two objects, not a property of one. That's all I'm talking about right here. But okay, the formula. Okay, since we have like 5 minutes, I'm going to quickly, but this is great. And even I'm going to say this in 5 minutes, what I think the resolution is, you might not think it's that exciting. The first goal is to just think it's clear, but even if you don't think it's clear, you'll have time, like a full weekend to think about it. Okay, here's a okay. Right. What is key is that lambda WS must equal lambda WR, right? Wavelength of wave according to source must be the same as wavelength of wave according to receiver. But, so that's true. And you use that in every one of your cases. But okay, very quickly, with like 2 minutes left, first thing I want to say is, no matter what the wavelength is, the source and the receiver must agree on it. But if the source is moving toward the receiver, the wavelength is different from if the source is stationary in the medium. If the source is moving through the medium, as a couple people put in the direct chat, or in different ways, a number of people put, if the source is moving through the medium, sure. If the source is moving through the medium, say approaching the receiver, then it sends out a wavefront, and then it waits a certain amount of time to send out the next one, a certain fixed amount of time. But during that time, it's still going forward, like as people in the direct chat were saying. So the next wavefront comes out closer than it otherwise would have. So what I'm trying to say in short is, in the case where a source moves toward the receiver, we send out a compressed wavelength with, yeah. Oh, here, okay, so let me just, okay, well, I'm just gonna write this in a second, but hold on. And we are gonna wrap in this, what does this say? What just happened? Hold on. Oh, go for it. Yeah, okay. In fact, can I go forward even more? Can I start a new page, or? All right. What I'm saying is, when the source moves, say, toward the receiver, we send out a shorter than usual wavelength, and then the receiver receives the shorter than usual wavelength at a usual speed. Like that is the the receiver's just sitting there in the medium. So the wavelength comes to the receiver at the customary speed of, in this case, 340 meters per second, right? If the source is moving, what we get is a distorted wave. I shouldn't say distorted. We get an altered wavelength coming in at us at customary speed, as opposed to when the receiver moves toward the source, we get a customary wavelength, but we catch it at a non-customary speed. It's a different phenomenon. I'll say that one more time, and you'll have to write this down because we are going to. I'm saying, if the receiver is moving toward the source, that why there's a Doppler effect is the receiver is receiving customary, expected, typical wavelengths. They haven't been affected at all, but the receiver is receiving those wavelengths at a non-customary speed. Like if the speed of the wavefronts is 340 meters per second relative to air, but the receiver's moving through the air at 44 meters per second, then the receiver is receiving these wavefronts as though in a blast of wind, right? Regular everyday wavefronts are coming in at the receiver faster than usual. That's if the receiver's moving relative to the medium. If the source is moving relative to the medium, the receiver doesn't receive the medium. The receiver doesn't receive the wavefronts at any kind of unusual speed. The receiver will receive the wavefronts at exactly 340 meters per second. However, those wavefronts will have already been compressed by the fact that the source was moving. So I'm going to say this one last time in English. I'm saying it's actually two different phenomena. When the receiver moves toward the source, the receiver receives customary wavelengths at a non-customary speed. When the source moves towards the receiver, the receiver receives non-customary wavelengths at a customary speed. In one case, this whole shift is happening through the wavelengths. In the other case, it is not. No matter what, source and receiver always agree on the wavelength. They'll agree on what the wavelength is. It's just that the wavelength, they might agree on a wavelength that's an unusual, unexpected number. If the source is moving, I'm going to say, okay, and I could say that again on Monday if you want me to, or you can replay the video or whatever, but why do I even care? Like, who cares? Like, so what? Maybe if you really think about it, it's like everything else in physics. Maybe now that you hear that, you might be like, well, I kind of knew that the whole time. Is that the whole issue? So what? What this is really saying is this, and this is where we're going to end. We're really saying one of the things that the Doppler effect is already interesting, and it's common. We hear with motorcycles all the time, and it turns out to be a very powerful way to measure things, and it has to do with outer space and the expanding universe and all that. But the fact that the Doppler effect happens at all is one thing. The fact that the Doppler shift for a receiver moving is different from the Doppler shift for a source moving, what that reveals to us is the reality. It reveals to us the vital role played by the medium, because relativity is still relativity. Absolutely, it is still true that if I move relative to you, that is equivalent to you moving relative to me. However, everything I just said about the wavelengths and all of that, if you step back and think about it, what we're really saying here is this. The relation that's happening here, the relativity that's at play, is not the relation between source and receiver. That's not it's not that source to receiver is the same as receiver is to source. What it is that source to medium is the same as medium to source, and receiver to medium is the same as medium to receiver. What we're saying here is that the medium is as valid a frame of reference as any other object, as any other thingy thing, as any other particle. The medium plays just as much of a role as a frame of reference as the source does or as the receiver does. Once a wave is involved, is being thrown from one object to another, there aren't just two objects involved, there's really three. The third is the medium. The medium is that real, it's that vital, it's that intrinsic to wave motion. That's what I'm trying to say. If you need me to repeat that on Monday, I will. Oh, okay. Oh, cool. Awesome. I see what's in the chat. Great. I'm glad you discussed this in the board meeting. That's awesome. You've been very patient. I'm going to go now. you chat. I mean, you can text me or email me with questions. Again, there's nothing. I'll post more videos later, but the homework is exactly like this lab thing. So just do it together and hand it in. And you've been great. And cheers, everybody. Goodbye.
Bye,
Thank
Professor.
you. Bye.
Thanks.
Thank you. Thank you.
Have a nice day.
You too. Thank you. Awesome. Bye. Great job. Thank you guys. Awesome. Okay, if you guys are cool, I'm going to post this right now, but I'm going to leave unless you have a question right now. Mario to Weeba, I'm taking off unless you stop me right now. Okay, going one. Oh, you good? Okay, great. Okay, Mario, you're good. Going once. Going twice. All right. Thank you.